Okay, so first off, I have a question. What's the equation for the tangent line? I'm gonna choose something at random.
The derivative of the original function.
Yeah, well, the derivative will be involved, certainly, right? The slope of the tangent line, right? So a slope is going to be f prime c, right? Certainly, that's the slope of the tangent line, right? What's the equation of the tangent line? I'm gonna choose something at random. Allie.
Is it delta x minus, or yeah, f of x equals delta x?
What's delta x? What's delta?
Or the change in x?
Okay, so x minus c, maybe?
Yeah. And then over. Wait, no, it's delta x minus c, and then minus f of x over h.
What's h? What's h?
The like area in between the f of x and then the f of x plus h.
So all I want is the equation for this line here, right? Right. I want the so like you know the slope of this line, right? The slope of this line is f prime. Okay. Right. Here's this is the graph of f, right? And so if you're describing a line, then here we've got a point, right? And you've got the slope. What's the? Can anyone tell me the coordinates of this point? I'm gonna. Somebody tell me. Yeah, Sarah.
C, comma, F.
C, comma, F of C. Great. So I'm gonna try and call on people who don't normally talk. Those of you who normally talk are banned from speaking. Okay, but you should be proud. You know, that's a good thing. You should be like, I've been banned from speaking. It's a badge of honor. It's not at all like a disapproval. It's good. It's good. Okay. Okay. So there's this point here, right? You've got the point and the slope, right? So how do you describe this thing? Right. You could say y minus. Allie, do you want to do it or?
I think I'm doing it the wrong way because usually aren't you supposed to look for the area or like the x in between the 2 points? Maybe I'm thinking of a different equation.
So all we have.
Like if you have
Yeah.
a c and f of c, then you're looking for the like c in between or the h in between the 2 points on the x-axis.
But there's only one point on the x-axis, right? So maybe you're thinking about if you have two points on a line, and you want to describe that line, right?
I just remember like in one of the recent sections we did it with like an h, and then you were asking about the h in between the 2 points. Maybe it's with 2 points. I don't know. That's
Okay.
probably why I'm confused.
Okay. Well, yeah, don't worry. It's so just remember we have this thing, the point slope formula, right? Which says that you're gonna take if you have a point x naught y naught, and you know the slope. Suppose you know that the slope is say m, okay, yeah, and you have some line, and you know the slope of that, right? Then the equation for the line is going to be y minus y naught equals m x minus x naught, right? That is to say y equals m x minus x naught plus y naught. Okay, so I hope you remember this from the beginning. We did this at the beginning of the course. Right? You know what this is saying is that y minus y naught over x minus x naught is m, right? That the change in y over the change in x. If I divide both sides by x minus x naught, you know what I get. This is the same thing as saying that y minus y naught over x minus x naught is m. that the change in y over the change in x is going to be some fixed number m. Okay. So over here, what you're going to get is that y equals f prime c x minus c plus f of c. Right? The slope times x minus c plus the plus x minus the x naught plus the y naught value. Is everyone okay with that? Yeah. Feel free to say I'm not okay with that. Yeah, Luke.
But the y naught value isn't the y-intercept, is it? Like why is the y naught value b? If you're
It's
putting it, oh, never mind. Okay, I see it now.
yeah. This isn't slope-intercept form.
Oh, okay.
This isn't slope. This is not the y-intercept.
Yeah.
This is the y coordinate of your point. Yeah, review your lines. Okay, so you have this thing, right? So what's the equation of a tangent line, right? So L of x is this guy, f prime c, oops, f prime c, x minus c, plus f of c. Okay. Right. Okay. So okay. So that's the L of x, right? That's the equation. That's the equation for the tangent line. And let's just put it in and see what happens. Okay, right? Let's just put it, or maybe I'll let you do it. Put it in. Take 1 minute. Put it in and see what happens. Okay. Look at f of x minus L of x over x minus c as x goes to c. Let's see what happens. You see that something nice happens.
Wait, why isn't it just c times f prime and c? I'm so confused about that.
What are you confused about?
For the tangent line?
The tangent line,
why isn't it f prime of c times c.
Times c.
Yeah. If you're trying to find the tangent line at c.
Okay, so what's the slope? Right, the slope is f times c.
Yeah.
Right. This point here is c. Right. This point here has coordinates c, f of c.
Yeah.
Right. So, what's the equation for the line? Y minus y naught equals slope x minus x naught.
Okay.
Right.
Just add it.
Right, yeah.
Right. Y minus y naught equals slope x minus x naught. Okay, turn to somebody nearby and say, here's what happened. Okay. I should say that when I first arrived at Scripps in the spring semester of 2006, I was assigned to teach a pre-calculus course. And there were students in that pre-calculus course who maybe couldn't add or couldn't do fractions and things. And I was sort of shocked by it. And whenever this sort of problem occurred, I'd look at them like this. After a while, I realized that that's not a helpful expression. Like, like, my God, you know, you don't want it as a teacher. You want to be completely blank, basically. Like, that's a very interesting way of thinking. Yeah, but yeah. So I hope. Sorry if I look surprised every once in a while. But if I look like this, I just tell me to to please blank my face, and I'll try to blank it. Okay. For you, Evan, that's for you. You know, because I probably looked at you like that just now when you asked.
Yeah, it's like.
Okay. Okay. So what happens? Somebody want to tell me? Somebody who doesn't normally talk. Cole. Great.
The x minus c on the bottom cancels out.
Yeah. So you get, let's see, you get f of x. The L of x turns into, so you subtract f prime. I'm going to sort of change the order. You subtract f of c, and you subtract f prime c, x minus c. And the whole thing is divided by x minus c. That's x minus c. So what happens? What cancels off?
The x minus c.
Well, I can't just cancel off of that guy. I mean, let me split it up first, okay? Because I've got to minus f prime c, x minus c over x minus c, right? So you can't just like, if I have a plus b plus cd over d, I can't just cancel off the d's, right? It has to be a plus b over d plus cd over d. Then I can cancel off the d's, right? Because the factor has to be on the whole thing. Okay. So what happens? These guys cancel off, right? And you get f of x minus f of c over x of x minus c minus f prime c, right? Well, what happens to that? Somebody want to tell me, other than the regulars? Shannon. Amanda, you are a regular.
If f of x goes to c, then doesn't it become like f of c, so that cancels out?
Yeah, this becomes f prime c, right? This becomes f prime c. So when the x goes to c, you get f prime c minus f prime c, which is c. Okay. Right. F of x minus f of c over x minus c. As x goes to c, that's the derivative, right? Okay, remember this was the other form. Remember, one form was c plus h minus f of c over h, and then the other form was f of x minus f of c over x minus c as x goes to c. Right? There were two forms of the two ways of expressing the derivative. This was one of them. This is the derivative. Okay. Yeah, Nico.
So, just like, how do you, in the big picture, like starting the problem? So,
Yeah.
Like sometimes it seems like in order to do these proofs, you kind of like have to go on like a random different path, and like it would be hard to know.
Yeah. So that's good. So let's think. Like now that it's done, you want to look back and think, would I be able to do this, right? Or how would I be able to do this, right? You say, okay. Somebody gives you this problem where Lx is the tangent line, okay? So the first question is, you'd say, well, would I be able to find the equation for the tangent line? Hopefully, yes, right? You know how you've taken equations you've done equations for tangent lines before, right? You get the slope, you have a point, use the point slope formula. Okay, so I think that part should be okay, right? And then you plug it in. Right, and then after plugging it in, I think it's pretty straightforward, right? You plug it in, and then you do some arithmetic, and you see that you get 0. So think about what's the hard part. What was the hard part? Finding the tangent line. Okay. So, what was the hard part about finding the tangent line? You, Isaac.
They weren't the regular x's and y's, so I didn't.
They weren't the regular x's and y's.
So it wasn't like, oh, x plus x naught. Well, it wasn't like x plus the delta x plus y plus.
I see. I see. But at least you have the point. You have the point and the slope, right? You've got this point on the line. You've got the slope on the line. So maybe it's sort of a lack of, like, you want to be very comfortable with the expressions of lines, right? I think that might be the sticking point for a lot of people. Like, a lot of trouble is that people get hooked on slope-intercept form. Like, for some reason in junior high school, lines are always y equals mx plus b, y equals mx plus b, right? But you know, there's a lot of good forms, and this is actually probably the most handy one, right? Slope point slope. So lose your attachment to slope-intercept form. And be able to translate back and forth, and definitely don't be attached to slope-intercept form, because that's very particular. Nico.
Well, what I was sort of saying is that I like didn't think it was intuitive to figure out what the tangent line was.
Oh.
So I like, if it, in general, if you say something like that, are we to figure out what that is?
Well, I think it sort of would be pushed on you, right? If somebody says, show that this is equal to 0, right? Well, how are you going to think about it, right? You have to say, what is this, right? If you can't express what this is, then how are you going to think about how are you going to think about it, right? So, you know, part of solving problems is just asking, do I actually know what this is, right? You have some function, you know, you have this function, it's evaluated here, blah blah blah, but you know, do I actually understand what this is? Well, I actually can write down what it is, right? So, yeah, that's useful certainly to write down an expression for it, write down an alternate expression for it. Okay. Yeah.
Isn't the alternative formulation of the derivative?
I'm sorry?
Isn't this the alternative formulation of the derivative proof?
I mean, it's certainly, this is another way of expressing f prime c. Yeah, but this, what we just showed is not, is something a little bit different from that. Yes. What we just showed is that something very special about the tangent line. Okay, what we just showed is this. Right, look at this, okay. This is really, I'm sorry to take so much time on this, but what if I said something like this? F of x minus L of x equals 0 as x approaches c. Well, what does that say in English? What does it say about the tangent line?
The function is equal to the tangent line?
Well, as x goes close to c, right? As x goes to c, the function and the tangent line get close to each other, right? So that's basically saying that the distance between them gets small, right? The distance between the line and the function gets small, okay? But what we're saying is something a little bit better than that. That even if you divide it by x minus c, it still gets small, okay? So this is basically saying that it gets small. The difference decreases quickly. Decreases quickly. Okay. It's a sort of a comment about how fast it happens. Okay, because Okay, I could keep on talking, but I don't want to. No, I'm gonna say one more thing. Sorry. Okay. So here's the last thing we're gonna say. Suppose I have a graph like this, and the tangent line. If I look at this, what do I get? I look at the difference as x approaches c. What happens to that difference?
You get small. You get small.
It gets smaller, right? It goes to 0, right? It goes to 0. Right? But you notice that this graph isn't differentiable, right? And what if you work it out, if you divide by x minus c, it doesn't go to 0. Okay. So that's sort of the difference, that with a differentiable graph, even when you divide by x minus c, it's going to go to 0. Okay, I'm going too far on this. Okay. But this is key, but I shouldn't talk about it. Okay. Okay, so 3.4, let's go on. Basic derivatives. Basic derivatives. Okay. So first thing is that recall that because of Pascal's triangle, basically we got the power rule, right? Which said that the derivative of x to the n was n x to the n minus 1, as long as n was a natural number, right? N was 1, 2, 3, etc. Okay. So right now I'm just going to state a fact, which is that the power rule holds for all numbers, all real numbers, all powers. So that is, if you differentiate x to the p, you're going to get px to the p minus 1. Even if that number is, a fraction, a negative number, an irrational number, whatever, it's still gonna hold. And we'll see why shortly. But right now, I just want you to know it. So, for example, if I say f of x is the square root of x to the 5 minus 3x to the minus 7, well, you can use the power rule on this and get the derivative. So f prime, you just use the power rule. Okay, so try it. Take 20 seconds and write down. Take 10 seconds and write down the answer. Take 0 seconds. You've already written down the answer. Getting all low numbers today. I'm not in you, right? So what happens to this one?
-5x with
So this is the square root of x to the
One.
fifth. So this is x to the 5 halves. So you get
5 over 2x to the first -7.
nope, just subtract 1 from it, right? So 5 halves x to the 5 halves minus 1, right? Which is 3 halves. Okay. And then the second part, what do you get there?
Straight on x is -8.
Right. So you just subtract 1 from it. Okay, so bring the power down and take one away from the power. Okay. Okay. So that's pretty simple, right? You've seen the power rule before, and right now I'm just going to tell you as a fact, but we'll explain why in a second, that it works for all numbers. Okay. Everyone, Corinne, are you all right? Okay. Here's another one that's going to be important. E to the x, the exponential function. Those of you who've seen this before, don't answer. but what do you think? What do you think happens to this? Those of you who haven't seen this before, what do you think happens? Do you have an idea what happens? Ellie?
Doesn't it become a natural log? Or ln e? Or ln x?
No. So the natural log will be the inverse function. Will be the inverse function of it, right? E to the x looks like this, and then the natural log is going to be this sort of thing. But it's not the derivative of it. Yeah, at least.
Is the derivative the same function?
Yeah. So that's the thing. It turns out that the derivative of e to the x is still e to the x. Okay. Yeah, and you know, when I was in graduate school, like a graduate student from Greece said, he told me this joke, and he said, it was, I still can't, I don't see what's funny about this joke, but you know, it's like there's a bunch of functions in a train, and everybody's in a panic, blah blah blah, because you know the differentiation is coming by, but there's one function, and he's you know, he says, I don't care, I'm the exponential function. That's the end. Yeah. Anyway, so yeah. Anyway, you like that one?
Yeah.
Okay. Very good. Very good. But actually, this guy from Greece was very smart and very humorous. Contrary to evidence. I once asked him what Greeks say when, you know, like in English you say, it's Greek to me, right? It's Greek to me. What do Greeks say? Does anybody know? They say, it's Chinese to me. Anyway, enough chit chat. So the exponential function is the only function that has this property. And let's think about what it means. Let's just think for a second geometrically what that means. Okay. It means that if I am here at some point x, at some point c, say, suppose I'm at some point c, then, right, the height here is, if this is the exponential function, then the height here is e of c, right? So I mean, that's nothing so far, but what's the derivative here? What's the slope here? E of c also, right? So the slope of this line, slope of the tangent line, is e of c. You laugh. Why? I'm not sure. Okay. Is also e of c, right? Now think about what that means. Suppose I draw the tangent line down to here. I intersect. What is this point here? If the slope is e of c, right? If the slope is e of c and the height is e of c, then if I draw the tangent line down here, how far have I traveled? What's the change in x? What's the change in x? Somebody said it? No? Evan, you are bad also. Isaac? Okay, go ahead.
Is it 1?
It's 1. Very good. It's 1, right? Because, you know, the slope, right? The height here is e of c, right? The slope is e of c, so that means that the change in x must be 1, right? The slope is going to be the rise over the run. The slope is e of c, the rise is e of c, so the run must be 1. Okay, so this length is 1. Okay. Now, if we take another point on the tangent line, we do the same thing. Well, this is just c. This is another different c, and the point of intersection of the tangent line with the y-axis is again going to be 1 unit away, right? If I do it here, same thing, it's going to be 1 unit to the left, right? So this is a very funny thing about the tangent line. That's what this is saying, that if you take tangent lines, then no matter what tangent line you take, it's always going to intersect 1 unit to the left. Okay. And the exponential function is the only function that has this peculiar property. In terms of velocity, what this is saying is that your position is the same thing as your velocity. Okay, so if you're riding the exponential car, then if you've traveled 1,000 miles, then your speed is 1,000 miles per hour, right? Or 1,000 miles, whatever your units are, 1,000 miles per hour, right? And once you get to the 2,000th mile, you'd be traveling 2,000 miles per hour. So your car, the speed of your car is exactly the same thing as your position. Okay. 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 So why does that happen? Let's look at the limit of e to the x plus h minus e to the x over h as h goes to 0. The derivative of e to the x is this. Right. So what do you get? E to the x plus h, that's going to be e to the x times e to the h. Right? E to the x times e to the h. Right? Okay. And then we actually can't show the whole thing, but let me give you some indication of what happens. E to the h minus 1 over h. Now you can factor out e to the x out of both of these guys. Okay. And so what you get is that it's going to be e to the x times this limit, e to the h minus 1 over h as h goes to 0. So the derivative of e to the x is e to the x times some constant. Okay, and it turns out that this constant is equal to 1, but we can't show that yet. Okay. Okay. Any questions, Newer?
Sorry, so that whole thing equals 1?
Yeah. So you get e to the x times 1.
Okay.
That thing in the parentheses equals 1.
Right.
Yeah. No.
Isn't what that's saying at the right-hand corner? Does it say equals 1?
Equals 1.
Okay.
Yeah. Sorry. Yeah. So this thing actually equals 1. Okay. Okay. So, for example, if I asked you to take the derivative, just for exercise, I'd like you to differentiate this thing. Okay. So take 1 minute and differentiate. Okay, turn to somebody next to you and say, this is how to do it.
Oh, you just define quotient rule. Yeah, so this is just basically this is like these are the two derivatives. Right.
Okay, okay. Who would like to say how to do it? Or should I choose somebody random? Probably should. Maureen.
So I did quotient rule.
Yeah, quotient
So
rule.
I did the bottom, so e to the x minus 1 times the derivative of the top, which is just e to the x,
Mhm.
minus the top times the derivative of the bottom, which is again e to the x,
Yes.
and then it was all over the bottom squared, so e to the x minus 1 squared.
Yeah, so it's easy, right? So just use the quotient rule plus your new knowledge about the derivative of e to the x. Sorry, Marie, I just went crazy for a second. Luke,
Would you mind simplifying it? Or?
if you'd like. So you get e to the 2x minus e to the x minus e to the 2x minus e to the x over e to the x minus 1 squared. Right? And so you get negative 2 e to the x over e to the x minus 1 squared. Okay. Other questions? The other day there was a workshop on like controlling your class and what do you do if a student is talking too much. I didn't say, but I should have said, well, in my class I just simply banned them from speaking. Yeah, but I think they were talking more about like humanities classes where there's some student who talks a lot. Okay, last exercise. F of x is x to the p. I'm not really sure why this one is in here. Oh no, okay, it makes sense. X to the p, x squared minus 1, and p is between 0 and 2. Okay, at what points does f have a horizontal tangent? At what points does f have a horizontal tangent? Okay. So again, this is something entirely within your grasp. So just we've got 3 minutes left. Take 2 of them and see how far you can get on them. Okay. Since there's not much time, let's just talk it through. So at what points does f have a horizontal tangent? So what do we need to, how do we translate that question into yeah, Kayla?
At what point is the community equal to 0?
Right, so this is the same thing as asking where is f prime x equal to 0? Okay, so we need to take the derivative. So you take the derivative, you say, okay, bottom times the derivative of the top. Kayla, tell me what it is, just for exercise.
So, x squared plus 1 times p x to the p minus 1
Mhm.
minus x to the p times 2x all over x squared plus 1 squared.
Okay. So the question is, where is this equal to 0, right? So we've changed the question again. We've translated our question into this question. You know, where is this thing equal to 0? Well, that thing's going to be equal to 0 wherever the top is equal to 0, right? We don't have to worry about the bottom. Right? So the question turns into, where is x squared plus 1 p x p minus 1 equal to 2x to the p plus 1? Right? Where is the numerator equal to 0? Right, so I set the top equal to 0. Okay, and did anybody finish it? What should we do from here? What could we do from here? And one thing we could do is maybe divide both sides by x to the p minus 1. Right? And you end up with x squared plus 1 times p equals 2x squared. Right? Because you got x to the p times x, and you've got x to the p times x to the minus 1 on the bottom. Right? So that becomes x squared. Yes? Okay.
So it's using equal to 0, so then it becomes 2x p to
So we have x squared plus 1, p x to the p minus 1, minus 2x to the p plus 1 equals 0. Right? I'm setting the numerator equal to 0.
how did you get x to the p plus 1?
Because we've got x to the p times 2 times x. Right? So x to the p times x is going to be x to the p plus 1.
Oh, okay.
Right? And then you've got the 2. And then so I move these guys to the other side, right? And then divide, you end up with this. So you get, moving this back, maybe I shouldn't have, let's move it back now. So px squared plus p minus 2x squared equals 0. In other words, p minus 2 x squared equals negative p. Right? So x squared is going to be negative p over p minus 2. So then you take square roots of both sides, and you see that x can be plus or minus the square root of this number. And that would be the answer. So, right, so again, this is just a matter of translating your problem using the quotient rule, and then just doing some you know, like pre-calculus solving for the points. Yeah, Isaac.